Hello. Today we'll figure out how to find surface areas of pyramids and cones. There's a lot of vocabulary here, but there's only a couple of things that are kind of new or different from what you'd expect. For instance, one of the things that's not different is the top pointy part of the pyramid is called the vertex. Well, if this were just a triangle all by itself, this would be a vertex, wouldn't it? So, this is the vertex of pyramid. These two are more important. This is the height of the pyramid. For surface area, we might use it to find other parameters, but we won't use it directly very much in surface area. But later, when we compute volumes, we will definitely need this height. And that's what it's called. So this right here, this is called the height. Put an H there. The height of the pyramid. The perpendicular distance from the plane that forms the base here, or the perpendicular distance from the base to the vertex. What about this? Slant height. Well, so what we're calling the slant height of a pyramid, that's what we used to call the altitude of this triangle. In other words, we have a triangle here that forms one face of this pyramid. The slant height is the altitude of that triangle. It's called a slant height, I guess, because the triangle itself is slanted. But if we were just take this triangle right here and cut it out or peel it off, remove it from the pyramid, so we just have this triangle all by itself, it would be like this. And this blue line here would be what we used to call the altitude of the triangle. In other words, if we wanted the area of this triangle, well, if we wanted the area of this one, it would be this height times the base times 1/2, or 1/2 of the base times the height. Same thing here. The slant height is in fact the height or altitude of the triangle. So the area of this triangle would be this base times the slant height times 1/2. So we get right at 1/2 times the side length times h sub s, which is just what I'm using for slant height. Which is exactly the same as this thing over here. So if we wanted the area of this pyramid, well, it's starting to look kind of obvious, isn't it? If we had 4 congruent triangles here, let's suppose we do, because we have a square here. This is a square pyramid, so each of these triangles would have the same base. Unless they're tilted in a strange way. If we have the same angle with the base for each triangle, then these are all going to be congruent triangles. So all we have to do for this regular square pyramid is take the area of the triangle, multiply it by 4, because there are 4 of them, which are all congruent, and the surface area of the base, which of course would just be s squared. So for this entire pyramid, it would be pretty easy to work out the area. You just write, say, a sub p for the pyramid. Well, that's the area of the base, which would be s squared, plus 4 times the areas of each of these triangles, which is 1/2, times s times the slant height. We'll call that h sub s. And that's all you had to do. Of course, you could just turn this into a 2, cancel it, and you'd have a more standard looking formula. And of course this part here, this is just the base, right? So we could write a sub b for area of the base, whatever it is. plus. Well, this is where it gets tricky, because the base might be a triangle, a pentagon, hexagon, any n-gon. So we're going to have to take the number of sides. We'll have one triangle for each side. We got 4 sides here, so we have one triangle connected. If we had a pentagon, we'd have to attach 5 triangles. They'd all lean in and meet up right here at the vertex. So it's n times 1/2 side plus the slant height, h sub s. This is the general term where you could actually have another triangle for a base, in which case you would only have 3 triangles on top. You'd have a tetrahedron. This formula is general, and it works for all pyramids, hexagonal, square, whatever you've got. This part for a regular is much easier for a regular polygon that forms the base. If you have an irregular polygon, everything gets more complicated because the triangles won't be congruent. They can't be. They have to have different side lengths here. But with regular n-gons, you can use this. You find the area of one triangle and multiply it by the number of sides which your base polygon has. It sounds weird when you say it. We're going to work some problems, and this will be even more obvious than it already is if it's not super obvious. And there's one more thing. If we happen to have, what would, if I rearrange this as just this part here, 1/2 ns times h sub s. Well, what is ns? That's the perimeter. That's the side length, and that's the number of sides. N is the number of sides, s is the side length. So we can write this as p times h sub s times 1/2. This works in those happy times when you actually have the perimeter ahead of time. I don't know how often that would actually happen, but if you do have the perimeter, naturally you can skip this, not worry about what the side length is or the number of sides, just use this. However, when it comes time to compute the area of the base, I think you're going to need to know how many sides it has, because hexagons and squares have completely different formulas for computing areas. Although there is a general formula for the polygon. Remember that one? When we, suppose I draw a little hexagon up here. Very little. And then we put a center here and figure out what this angle is. And using a side length, we can compute the area of this triangle, and there's 6 of them. And you can do that for any polygon. So in general, that's probably how you'll be computing the area for the base for larger polygons. But if you're given the perimeter, you can use this formula here. Now for a cone, we have some very similar parameters going on here. Instead of a side length, we have r, because the base of the cone is, of course, a circle. The distance from the base to the vertex is the perpendicular distance. That's the height, just like it was with the pyramid. And from the vertex to the circumference here, that distance, that's the slant height, just like before with the triangle. We have a height which is, of course, a bit different from this one. And it's pretty obvious also that if we were to draw r from here, where our height meets up with the base, out to where the slant height hits the circumference, we would form a right angle here, and this whole thing would be a right triangle. Which means if you've got a couple of these, it's pretty easy to find the other one. For instance, the slant height, h sub s, would just be h squared, whoa, plus r squared and the square root. Pythagoras. This would be that squared plus that squared, and then you take the square root. So these parameters are going to be fairly easy to find as long as we remember Pythagoras' theorem. When we want to find the surface area of this thing, well, this part's pretty easy. This is going to be pi r squared. I don't think you have any trouble seeing what the surface area of the base is going to be. But this thing here, this lateral surface, it's kind of weird. It's not going to be, if we were to unfold this and produce a net, this part here is definitely not going to give us a rectangle like it did with the cylinder. It's going to be quite a bit different. So if we cut this and unwrap it, so to speak, we're going to get something like this. Boy, when this folds up and becomes three-dimensional, this part here is going to be at the vertex, and this part is going to wrap around this circle. That's why I wrote 2 pi r. The distance is to say the arc length of this arc from here all the way around to here. That's 2 pi r because it has to wrap around this circle here. This is the part that touches the base. Remember, r is the r for the base circle. This big circle here, which is what we get when we unfold this thing, well, it's not quite a big circle, is it? It's a big circle with a sector taken out of it. Or we could say that this was the sector. And in fact, if we want to find the area of this big piece here, it's quicker and easier to consider this big piece as the sector. And the area of this piece will be the same fraction of the whole area that this arc length is of the whole arc length. Or, to put that in more mathematical terms, we take the area of, call it the lateral surface, a sub l. That would be the area of this big circle, let's call it a sub c, times 2 pi r over 2 pi h sub s. When we make this cut here, our slant height is the distance from the vertex to the circumference of this circle. So this slant height is the radius for this big circle. It's easy to get confused here. We've got an r for our base circle. We also have a radius for our large circle, and that is the slant height. That's why we use this here, down here. Well, what would a sub c be? The area of this great big circle. Well, that would just be pi times h sub s squared, right? And we're going to multiply that by 2 pi r over 2 pi h sub s. In other words, the arc length of this divided by the arc length of the entire circle. And that'll tell us what fraction of the whole area corresponds to the area of this sector. Well, a little cancellation going on right off the bat here, isn't there? We can scratch these 2 pi's, they cancel each other. We've got a slant height squared over here and a slant height here. So we can cancel one of those and end up with pi times h sub s times r. Remember, h sub s is the radius for the big circle, and the r here is r for your base circle. That gives us the area for this. If we wanted the area for the whole pyramid, naturally we just add in our pi r squared. That's the area of the base circle. So here we have a formula for the surface area of a cone. And cones are kind of important in mathematics. You wouldn't think so, but a long time ago, curves were studied as conic sections. In other words, if I took this cone and I cut it with a cross section parallel to the base, I'm going to end up with a circle, right? This cone does form a circle. I just get smaller and smaller circles as I go up. But since we've wrapped this all the way around, down here, if we cut it with the base, of course we get a circle which is exactly the base circle. As we keep going up, if we stay parallel to the base, we keep getting smaller and smaller circles. But suppose we don't cut it parallel to the base. Suppose we cut it at an angle. Then what are we going to get? Well, we're going to get something like this, aren't we? Turns out you can cut cones different ways to produce ellipses and hyperbolas. Pardon me. Hyperbolas. Hyperbole is when you use too many flowery words in your speech to make a point. Hyperbola is a particular type of curve which can be formed by cutting a cone at the right angle. So a long time ago, when, especially in algebra, when people studied ellipses and hyperbolas, they referred to them as conic sections. And if you want to see what it's like, Google conic sections. You can probably find a whole bunch of equations about what happens, or which tell you what happens when you cut a cone at an angle. But you're lucky. This is high school. We don't have to worry about that. All we have to know, this is not a problem we're going to have. All we have to know at the moment is finding the surface area. Later on, we'll be using this parameter when we need to find the volume of a cone. But right now, here's what we need for the surface area of a cone. Well, looks like our old buddies Inseam and Fleabite are playing with pyramids now. And of course they got it wrong again. They want to use 1/2 PL. I guess you could do that. That's just NS, right? Number of sides here is 4. And they have length 6. So 4 times 6 is 24. That part looks good. And when he took the area for the base, 6 squared, that seems right. The 1/2 in the front, that's formula for the lateral surface of the pyramid. That fits. And the 4, well, that's the... Oh, wait a minute. This is supposed to be the slant height, which is actually the altitude for this triangle. And that's what we're going to use, after all. The distance from the vertex to the base, what in the world would that have to do with the altitude of this triangle? It's not even part of this triangle. Well, we can compute it. They're related according to the Pythagoras theorem, but we can't interchange them. So this is supposed to be a 5. Since he multiplied by 4 when he should have multiplied by 5, there's one thing we could do. Suppose, just for fun, we took this answer and multiplied it by 5/4. In other words, if we took this whole equation, well, not the whole thing, just this part here, multiplied it by 5/4, the 4's would cancel, then I'd get rid of that 4, which is erroneous, and it would get replaced by a 5. So if we take 84 and multiply it by 5/4 instead of recomputing the entire equation, that should give us the right answer also. In this case, I don't know if it would save us much, but this part here is obviously 2 times 24, which is 48. cancel the 2, turn the 4 into a 2, that's 48. Multiply 48 by 5 over 4, and you get 60. If you add in this part, because this part was right, then we get 96. 60 plus 36 is 96. That'll give you the right answer. Or you could just stick a 5 in here. 5 times 24. That's 120, and half of 120 is 60. Probably no advantage to what I just did. Like I said, there's always more than one way to work a math problem. But the right answer, anyway, should have been 96, because this 4 should have been the 5. It should have used the slant height and not the pyramid height. Here's one where they asked us to find the lateral surface area of this cone. This may not be a particularly important problem, but I love ice cream cones, so that's why I'm doing it. The top part, the base, the circular base, we don't have to worry about. It doesn't have one, obviously, otherwise you couldn't get any ice cream inside it, couldn't you? Well, they gave us the height. Remember, that's the distance from the base to the vertex. That's not this distance here, but they gave us the radius. So if we were to draw it in, that's 1 and that's 4. We got 4 here, and this is 1. So what would the slant height be? Well, I think it would be the square root of 1 squared plus 4 squared. That would be the square root of 17. And that turns out to be 4.12. You see, this leg is pretty small compared to this one, which means that this hypotenuse here isn't much different from this, so the slant height isn't much different from the height. And if you did it the wrong way, using the height, naturally your answer isn't going to be very far off. Nobody would know that you actually did it wrong, except anyone who actually looked at the way you did the problem. But from the answer, if you were to compute this using 4 as the slant height instead of 4.12, your answer is going to look like it's pretty much right. From our formula, what do we get? Well, we get pi times r times the slant height. Now r is 1, the slant height is 4.12, so we just get pi times 4.12. And we get an actual answer of 12.95 would be the lateral surface of this delicious sugar cone. I think the conically shaped ones are called sugar cones, and those crummy ones, you know, the kind I'm talking about, that look like that, you know, like that. And then they have something that comes out here to make it easy to stick more ice cream into it. And then you put the ice cream in there, but they don't taste very good. I like these way better. No offense if your family makes these kind of cones. I'm sure there are people who like them. But as far as I'm concerned, this is the only kind of cone anybody ever needs. So to get this right, you just had to remember they used the slant height and not the regular height, and then remember your formula for the lateral part of the surface area of a cone. Well, looks like Inseam and Fleabite have been really busy today. They've done it again. The formula for the surface area of a cone is the base, the area of the base, plus the lateral area. The base, well, it's pi r squared. And r is 6, so what did they write? Pi 6 squared is 36. Looks good. What about the lateral area? Well, let's see here. That's pi, we figured this out already, times r times the slant height, which is this one here. Well, let's see here. They got the slant height. Okay. They got, oh, wait a minute. 36 is not the radius. Ooh, they squared the radius. That's no good. in this second part here, you got to get rid of the 2. It's just pi RL. So this should be pi times 6 times 10. So this is 36 pi, and this should be a 6, so this would be 60 pi. And this whole thing should end up being 96 pi, not 396 pi. So this kind of mistake, this would make a big error. Don't square this one. I don't know why he would do that, but one thing you might look at when you see something like r squared L, well, this is a length, r is a length, so you've got length squared times length. You end up with length cubed. Area always has to be the linear measurement squared. So if this were in centimeters, which it is, this would be centimeters squared times centimeters would give you centimeters cubed. Well, centimeters cubed is never going to be an area. You just can't do that. Cubic centimeters do not make up an area, only square centimeters. So you could also spot a problem with this without even knowing the formula. Because you're looking for an area, you got to end up with units squared. You can't end up with plain units, and you can't end up with units cubed. It's got to be units squared. That's the only kind of area that exists. At least it's the only one I know of. Well, this time they gave us the surface area, and they somehow expect us to figure out the slant height, the distance from the vertex to the circumference here. The circumference of the base circle. How can we do that? Well, what would the area be? Let's lay it out and maybe we'll have an equation that makes sense. This part here, let's see, 16, so it has a radius of 8. Okay, so we should have pi 8 squared, or 64 pi, plus, well, pi, remember, the lateral part of a cone is pi r, sometimes they call the slant height L, or h sub s for slant height. Well, that's pi times r again, which is 8, times slant height, which we don't know, and that's 200 pi. Well, I think the first thing we should do is divide through by 1 over pi and get rid of all these pi's. Next, subtract 64 from 200. HS times 8 is 136. Well, if we lay this out, 200 minus 64 is 136. 8 times the slant height is 136. We just divide through by 8 and get 17. Is that? Ooh, there it is. So the answer is B. Again, all we had to do was remember our formula for the surface area of the cone, lay it out, and then see what happens. And what happened is a lot of stuff drops out, and we get a pretty easy equation to solve. Here we have a regular pyramid with an hexagonal base. The edge length is 6. We can draw that in here, write it in, 6. And the slant height of 9 centimeters. Well, that's the distance from here to here, isn't it? Because this is the net for that pyramid he's talking about here. If we just open it up, fold all the triangles down, this is definitely not to scale. I mean, if this was 6, how in the world could this be 9? But the slant height is just what we used to call the altitude for this one particular triangle. for the whole pyramid, it's called the slant height. For this particular triangle, it would just be the altitude of the triangle. Remember, it goes like that. Well, okay, so this triangle, in fact, all 6 triangles, be pretty easy to find the area for these. And we can just use our pretty general formula for the area of a regular polygon. We just draw our little triangle out to the center, draw a line out to the center, forming a triangle. And we can do this 6 times. 360 all the way around means that this central angle here must be 60 degrees. That's this angle here. So half of that would be 30. Well, when we cut this angle, because these are both radii of this hexagon, we know they're the same length. We have an isosceles triangle. When we bisect the angle, we also bisect the opposite side, which means that we have 3 over here for a length of this leg of the right triangle we just created. And what we would like to find is this one. So we have that the tangent of 30 degrees, put it over here, would equal opposite over adjacent, or 3 over the altitude of that triangle. Well, tangent of 30, that's 1 over the square root of 3. So we can write, first we can write a equals 3 over the tangent of 30. But if tangent of 30 is 1 over the square root of 3, we just have to flip it and multiply and get root 3 times 3. Oh, okay, that gives us this length here. But the area for this triangle is going to be this whole side, that's 6 times the altitude, and then divided by 2. So if I put it over here, we'll write a sub p, how about a sub h, for the area of the hexagon. Well, then we get the altitude, that's 3 times the square root of 3, times the base, that's 6, and all that has to be divided by 2, of course. Well, 6 divided by 2 is 3 times 3, I get 9 times the square root of 3 for the area of the hexagon. That's this triangle multiplied by 6. Now the funny thing is, to get the lateral surface area for this pyramid, we're also going to find the area of another triangle and then multiply that one by 6. And that's an easy one. So a sub L, the lateral area, or all the triangles that form the lateral surface, I guess you could say. Well, it's going to be 6, because there are 6 of them, times 1/2 base height. Well, the base is 6 and the height is 9. So if we multiply all this out, the area for the hexagon is 6 times the area of this triangle, which is the altitude, 3 times the square root of 3, times the side length, which is 6, all times 1/2, of course. And that's 54 times the square root of 3, or 93.6. These triangles, of course, are going to be 9 times 6 times 1/2. And there are 6 of them. We multiply that out, we get 54 times 3, which is 162. So if we add those up, we get the total area and in the end we get a total area of 255.5. That would be The answer here, 255.5. First, you had to find the area of the pentagon, just using your generalized polygon area formula, and then take the area of one of these triangles and multiply by 6. Pretty easy. The main thing you had to remember was just some of your simple formulas from previous sections. Once you lay out the net, it's pretty easy to figure out what the surface area of an object is. Sometimes the hard part would be figuring out what the net looks like. But once you've got the net laid out, well, then you're just doing things that you definitely already know how to do. And here they've asked us to find the surface area of a regular tetrahedron with edge length 4 centimeters. So, remember, these are all the same triangle. This is the net. Badly drawn again. Each of these triangles should look just like this one. Well, it's going to be pretty easy once we figure out some more useful parameters. If we find the area of any one of these triangles, all we have to do is multiply by 4. So, what about this one? This is our altitude. Well, we have an equilateral triangle. That's because it's a regular tetrahedron. We also know that for equilateral triangle, the angles are all 60 degrees, which means half of that is 30 again. So we get 30 degrees here. This is the hypotenuse. That's 4. What we need is something that relates 4 and A. In other words, something over the hypotenuse would be good. In fact, this thing over the hypotenuse would be perfect, wouldn't it? We'll call that A. This is our altitude for this triangle here. Now let's see here. A over 4 equals what? A would be the adjacent side. Let's see here. Some old hippie. Sine opposite over hypotenuse. Well, that's not going to work. Cot another hippie. Let's see here. Cosine adjacent over hypotenuse. That's what we want. So we get the cosine of 30 degrees. So I can get that A, that's this height here, is 3.46. The base is 4. So the area for one triangle, call that A sub t, equals 1/2 of the base, that's 4 times the altitude, or 4 times 3.46. Or we can just cancel these and write 2 times 3.46. And that's going to be 6.9 something, right? 6.92. Sound about right. Well, there's supposed to be an equal sign in there. How about that? So one of these is 6.92. Now once I've got this, it's the area for one triangle, 6.92. I can write 4 times 6.92. That will be the total. That's 27.68. That's one way to do it. However, if I had drawn this net more correctly, it might be obvious that there's another way to do this. If I redraw this net slightly less badly, the existence of these straight lines might tell you something, because when you unfold this tetrahedron, what you're going to end up with is another big triangle. Why? Why would that be true? Well, these are all equilateral triangles. So this has a vertex, or an angle here, of 60 degrees. On the other hand, this is an equilateral triangle, In fact, it's the same equilateral triangle. They're congruent. But the important part is it's an equilateral triangle, which means this is 60 degrees. This is the vertex for another equilateral triangle, and here is a vertex of another one. Well, 60, 60, and 60 is 180. So this has to be a straight line. This is a straight line, and this is a straight line. Well, in that case, if this is 4, then each side here is 8. And if we wanted our altitude, we just drop a perpendicular down and just completely ignore this inside triangle here. Just find the area of this outside triangle, because that includes these 3 triangles plus the base. And the fact is, any triangle with a tetrahedron, turn it so that any one of these triangles is on the bottom, and you can call that the base, I guess. With a tetrahedron, the bases and the lateral surfaces are kind of hard to talk about because they're all the same thing. Well, this is 8, and this would have a side length of 4, of course. Well, now all we have to do we take our hypotenuse squared, subtract 1 leg squared, take the square root of that, and that'll give us our altitude. Similar to what we did before, but now we have 2 things to work with, the hypotenuse and the leg. So we can do it a little bit differently. We don't need any trig to do it this way. Not that that really matters, and nothing wrong with trig. So we got 64 minus 16. And I think that's the square root of 48. Okay. If this altitude is square root of 48, or I think I can write that as 4 times the square root of 3, that'll be 16 times 3. You pull out the 16 and get 4 times the square root of 3. That's this altitude here. If we multiply that by 8 and divide by 2, that'll be the base times the height divided by 2. So let's try that. We get 8. Now it's going to be a 1/2 out front here, times the base, that's 8, times 4 times the square root of 3. And guess what? You get the same thing, 27.7. If you actually try this, you might get a slight difference in the hundredths column. That's just because of round off, error using square roots. Kind of depends on how you carry things through. But they are equivalent. You could take these, add them up individually, as badly as that looks, or if you drew it more correctly, you might recognize that, oh, it's just one big triangle. All I have to do is find the area of the one big triangle we create when we produce the net of a tetrahedron. So you can do it either way. Well, that's about it.